or its asymmetry. Because with this anisotropy, this C axis can be pushed much faster than A or B. Not in all crystals, but in certain crystals, yes. So now I start applying pressure. So, and this pressure would be for all from all directions. Okay, it's completely isotropic pressure. But because of the anisotropy of this crystal, this fellow comes down at a much faster rate. So what's happening to my volume? My volume is decreasing, right? At certain point, since the C is reducing much faster, A, B and C will become equal. And then the special property of C no longer remains, that it will decrease much faster. Then all three, A, B and C would reduce at the same rate. So what I'll have is, this is called a tetragonal cell. From a tetragonal cell, I would transform into a cubic cell. But see, at the transition point, the volume does not change. It very smoothly goes over from this tetragonal to cubic. The rates of volume change could be different. Yeah, because here this fellow was being compressed much faster, and after the cubic all three are being compressed. They could have different rates. That's not a problem. But the volume would be the same. So if I were to plot volume, again everything will just say as a function of temperature. If we could have plotted as a function of pressure, no problem. It would. So all the derivatives of mu remain to be the same. So maybe something. Okay, it's continuous, but the slopes are different. It's a structural transition, that's it. Right? One crystal structure changes to another one. No, these are not allophories. This is just a crystal structure of certain compound. Okay. Mostly compounds, yeah. Right, so the slopes are different, which means that the derivative of volume would not be continuous. Right? Because that would be the slope of one, the other one would be the other. So the second derivative of mu would not be continuous in this case. And likewise, all of these. I mean, I could draw the same thing for enthalpy, entropy, heat capacity, right? Likewise, I could draw for all of them and show that the first derivatives are continuous, whereas the second derivatives are not. Okay. Good. So, do we have some more time? Yes. No, the first derivative of chemical potential is volume. Volume is continuous. The chemical potential would definitely change very smoothly. It will be a smooth curve. Its second derivative has to be discontinuous, which means the slope so the curvature has to be discontinuous, right? If it is going down at one place, at the other place it has to go up, or it's going right, then it has to change like this. The curvature has to change. So everything is given in these handouts. I mean, I've plotted one example each of these, so don't worry about that. Okay. Now, the thing is that we move on from single component to multi-component systems. And maybe I'll go a bit slow because I've taught up to this point in the morning class. So I get time, I get phased out, and then I have to do it fast over there so that we both keep it the same. both the classes are at the same place. So I'll just discuss that. Okay. Now, if you think of a multi-component system, let's try to define these quantities with respect to volume, because that is something more tangible, something which you can feel much easily, rather than to start with Gibbs free energy or chemical potential. So let me start with volume. And the thing is that, take an example. You have loads and loads of water, and you add 1 mole of water at standard conditions, standard temperature and pressure. Now, which is 1 bar, 298 Kelvin. I add 1 mole of water. What is the increase in volume of this entire load of water? That's 18 mil, right? 18 mil. 18 grams is the molar weight of waters, and 1 gram per mil is the density at standard conditions. Now 18 mil is the increase, but if I do the same experiment with ethanol, if I take a lot of ethanol, right, then it's 14 mil. We already have the notes. Good. So what is happening? Well, all these ethanol molecules, there are a large number of ethanol molecules, but a very small number of water. So my immediate neighborhood of water is not another water molecule, it's an ethanol molecule. And see, water forms all these different kinds of structures. I don't know if I showed you the phase diagram last time, did I? Or did I mention it? That there are these various 11, 12, 13 forms of ice. Right. So it shows all these different kinds of structures, and the way it is packed is like 2 H2O molecules. So one H2O molecule and another couple of H2O molecules next to it, forming kind of a tetrahedron, and then how it forms further just depends on the environment. The most likely structure is kind of a cage, which looks more like your benzene molecule perhaps. That kind of an open space in between. So there's an open space over there, right? That open space is not occupied by anything. And the moment you add ethanol, that gets rearranged. A more compact packing occurs. And because of that, instead of 18 ml being added to this pure ethanol, it's only 14 ml volume that gets increased. Okay. So I always say the molar volume of water is 18 mil, pure water. But the molar volume of pure water in ethanol, in pure ethanol, is 14 mil. Instead of saying the molar volume, what we say is that it's the partial molar volume. H2O in pure ethanol, okay? I'll underline, I'll highlight this word pure. And why I underline that is because this partial molar volume depends on how much ethanol I have. Okay. So if it's already a mixture of ethanol water, and I add now some amount of water, 1 mole of water in this mixture. Now remember that this addition is a very minuscule addition. I said I have a large amount of alcohol. Yeah. What? Is anybody happy about the fact that there is that? Okay. Now you've already diluted it with water. So this fellow is going to change. Okay, it will not remain 14. I can't reproduce that graph where you have Uh, um, how does it go? Oh well, I think it's better to see the notes if they are somewhere here. Ah, can I enlarge it? Okay. So if you look at that one, you have. I can't read the numbers. This should be 18, I guess, because that's for pure water. That's 0 mole fraction of ethanol. So that's pure water, and the molar volume of water is 18 mil, and that should be 14. Because when you have pure ethanol, then the partial molar volume of water is 14, and then it keeps on increasing. And it goes, something strange happens over there. We'll talk about that later. The same strangeness in the reverse way happens over here, and it keeps on. So if you see, if the partial molar volume of water decreases, the partial molar volume of ethanol increases, and the other way around. This is something very interesting, and